Pluto is a vast distance from the Sun, making it significantly dimmer than the sunlight that reaches Earth. This immense distance leads to extremely cold temperatures, dropping to around -230 degrees Celsius at night. However, during rare heat waves, temperatures can rise to as high as -170 degrees Celsius. Pluto also possesses a thin atmosphere, intriguing curious minds to explore beyond the natural boundaries of our solar system. Imagine if I told you that Pluto, the distant and enigmatic dwarf planet, is potentially on a collision course with Neptune, the ice giant. Pluto's rebellious nature has been apparent from the beginning, as it orbits on the outskirts of our celestial neighborhood. Its orbit boldly crosses that of another planet, challenging traditional notions of planetary behavior. Such behavior is indeed unusual for a planet. The complexities of Pluto's orbit and the concerns raised by astrophysical thinkers like Neil deGrasse Tyson and Michio Kaku lead to a lingering question. Will these celestial giants collide? Could their intersecting paths produce unforeseen consequences for Earth? Today, we embark on an exploration of this grand journey filled with uncertainty. While the answers to these cosmic questions may still elude us, the possibility of a collision of such monumental scale serves as a stark reminder that the universe is a stage for both awe-inspiring and potentially alarming events. Join us as we delve into the mysteries surrounding our understanding of Pluto and Neptune, contemplating the possible outcomes of a cosmic clash that could reshape the delicate balance of our solar system. The stage is set, and the unfolding drama beckons us to witness the mysterious dance of the planets. Among other potential cosmic catastrophes, the universe harbors a variety of puzzles, including the intricate riddle known as the three-body problem. Scientists anticipate other potential disasters within the celestial theater. Although the collision of one planet with another in space is extremely unlikely, it is not entirely out of the question. Gravitational interactions, as described by the three-body problem, influence planetary orbits. An example of a complex system where gravitational forces create periodic patterns, known as orbital resonances, is TRAPPIST-1, which features 7 planets similar in size to Earth. Over time, these patterns can destabilize planetary orbits, increasing the likelihood of collisions. Currently, no collisions are occurring, even in systems like TRAPPIST-1, which are densely packed, where planets can significantly influence each other's orbits, especially when they are close together. Scientists regularly monitor these systems to better understand their dynamics. This information enhances our understanding of how planets navigate through space. Another fascinating aspect of our cosmic landscape is the existence of rogue planets that drift aimlessly through space rather than orbiting a star. The ejection of planets from their star systems can occur due to gravitational interactions or other cosmic phenomena, such as the close approach of another star or the dynamic instability within multi-planet systems. Over time, these rogue planets can travel vast distances, potentially reaching areas far from their original locations, and could even encounter other star systems during their solitary journeys. The likelihood of a rogue planet colliding with another planet increases if one of these planets enters another planetary system. However, a head-on collision between rogue planets is highly improbable due to the vast and mostly empty nature of space. The sparsity of planets in open space and the immense interstellar distances discourage frequent collisions. While the probability of 2 rogue planets impacting each other is already low, the occurrence of rogue planets is even less studied compared to stable stars and planets. In the event of a cosmic merger, complex star systems can become turbulent. Nonetheless, it is highly unlikely that planets will collide directly during these grand events due to the vast interstellar distances. The orbits of stars and planets in forming galaxies are fundamentally influenced by strong gravitational forces, which can cause a planet to become a rogue body, cast into the cold depths of intergalactic space. Conversely, gravitational disruptions can eject planets from their orbits, leading to collisions with one another or even with their host stars. When gas and dust are compressed under extreme pressure, gravitational interactions can lead to the formation of new celestial bodies or the emergence of stars in our solar system. The late heavy bombardment suggests that approximately 4 billion years ago, there was a period of increased collisions involving comets and asteroids. This surge in impacts is believed to have resulted from gravitational disturbances caused by the outer planets. During this tumultuous period, gas giants like Jupiter and Saturn underwent migration, disrupting the orbits of various smaller bodies in the Kuiper belt and asteroid belt. Consequently, these smaller objects were thrown into erratic paths, with many entering the inner solar system. This deluge resulted in a significant increase in impacts on terrestrial planets, including Earth. While these impacts did not involve direct collisions between planets, they illustrate how gravitational interactions can cause major shifts in the trajectories of celestial bodies. This bombardment is thought to have played a crucial role in shaping the surfaces and geological features of planets within our solar system. Additionally, it may have contributed to the distribution of water and organic materials on Earth, influencing our planet's development over time. As stars undergo changes in mass, their planets can find themselves in altered orbits or even collide with each other. This is especially noticeable in systems where stars are nearing the end of their life cycles. As a star ages and consumes its nuclear fuel, it often experiences significant mass changes, particularly during stages like the red giant phase or when it sheds material in a planetary nebula. These fluctuations in stellar mass can profoundly impact the gravitational equilibrium of the system, causing the orbits of neighboring planets to either move outward or become more compact. This phenomenon is more likely to occur in multi-star systems, where complex gravitational interactions can easily lead to unstable orbits. In such systems, the gravitational forces from multiple stars can interact unpredictably, complicating orbital dynamics and increasing the chances of orbits crossing. This can result in scenarios where planets may be captured by another star, collide with other celestial bodies, or even be ejected into interstellar space. Pluto's unique orbit, initially recognized as that of a full-fledged planet, was ultimately reclassified as a dwarf planet due to its distinct trajectory. The astrophysical community remains fascinated by Pluto, finding it intriguing despite its renaming. Nevertheless, concerns about Pluto's proximity to Neptune's orbit have been raised by prominent researchers like Neil deGrasse Tyson and Michio Kaku. They point to a worrying possibility of a collision between Pluto and Neptune. Pluto's orbit around the Sun is unusual. It has not completed a full revolution since its discovery in 1930 and takes a lengthy 248 years to do so. This significant deviation from the generally circular orbits of the major planets makes Pluto's orbit exhibits fascinating characteristics, including an inclination of 17 to 28 degrees relative to the ecliptic plane. This combination of its elliptical shape and tilt adds complexity to its orbital path. A particularly intriguing aspect of Pluto's orbit is its intersection with Neptune's orbit. For approximately 20 years during each orbit, Pluto comes closer to the Sun than Neptune. This situation challenges assumptions based on their positions within the solar system and raises an important question. Why hasn't a collision between Pluto and Neptune occurred? The answer lies in the gravitational effects exerted by other planets. The assessment of Pluto's orbit began shortly after its discovery, revealing a complex path that differs from most planets, which have orbits more aligned with the ecliptic plane. Unlike these planets, Pluto has a significant tilt and an elongated orbit, which adds to the intrigue. The realization that Pluto's orbit crosses that of Neptune has led to further investigation into the dynamics at play. This situation is part of what is known as the three-body problem, which involves understanding the movements and gravitational interactions of three celestial bodies, Pluto, Neptune, and the Sun, predicting their orbits based on their initial positions and the gravitational influences they exert on one another is a complex task. Concepts like libration, orbital inclination, and the VZK oscillation help scientists tackle this cosmic puzzle. Astrophysicists view libration as significant since it helps maintain stable orbits. When Pluto crosses Neptune's orbit, it is approximately 90 degrees away, a distance that reduces the likelihood of collisions. Libration, which refers to the vertical movement of a celestial body in its orbit, ensures that Pluto remains significantly above Neptune's orbital plane, providing additional protection against collisions. A key factor in understanding celestial movements is the VZK oscillation, named after researchers Van Leeuwen and Kai, who studied gravitational interactions between three celestial objects like Pluto, Neptune, and the Sun. This oscillation helps explain why Pluto's orbit, despite its apparent irregularities, remains stable over time. Underneath the apparent randomness, there are fundamental patterns and rules that govern the celestial mechanics at play, maintaining Pluto's orbit and preventing collisions with Neptune or deviations from its path. The three-body problem helps illuminate how the gravitational influences of these celestial bodies affect their orbits, and studying this contributes to our knowledge of Pluto, our solar system, and distant celestial objects. Mathematical simulations from the late 1980s revealed that, despite its stable properties, Pluto's orbit is intrinsically chaotic, with minor initial deviations potentially leading to significant changes over millions of years. Nonetheless, Pluto's unusual orbit displays remarkable stability over long time spans, mitigating potential chaos. Recent computer simulations have advanced our understanding of the complex dynamics involving large planets like Neptune, Jupiter, and Saturn as they influence Pluto's path around the Sun. Neptune's distinct gravitational effect leads to 3 orbits for every 2 of Pluto, significantly contributing to the stability of Pluto's trajectory. While Jupiter's gravitational influence is present, it is less critical than that of Saturn. Overall, these observations demonstrate that Pluto maintains a stable and consistent movement through space over billions of years. This stability is safeguarded by the combined effects of Jupiter, Saturn, and Neptune, which keep the motions of celestial bodies in the solar system ordered and predictable. Without these systems, the solar system would be more turbulent and unpredictable, increasing the likelihood of collisions and perturbations from otherwise stable paths, with potentially widespread consequences for other celestial bodies. Considering recent theories about a possible collision between Pluto and Neptune, understanding Pluto's orbit becomes crucial. This knowledge enhances our comprehension of the ever-evolving nature of the solar system. Pluto's case illustrates how the intricate interplay between orbital mechanics and gravitational forces can bring seemingly unstable orbits into balance. To better grasp our place in the universe, continuous observation and exploration of these phenomena are vital. Space exploration often reveals the erratic behavior of celestial bodies, with Pluto's orbit serving as a classic example of orbital complexity. This phenomenon highlights how a celestial body's trajectory is highly dependent on its initial conditions, with minor changes in position or velocity significantly impacting its path over time. Researchers' understanding of Pluto's movement in space largely stems from computational simulations that utilize complex mathematical models to recreate the gravitational interactions among Pluto and other planetary bodies, like Neptune. These simulations illustrate how small alterations can lead to substantial effects on Pluto's trajectory. The models unveiled captivating aspects of Pluto's orbit in the late 1980s. Although features like libration and orbital inclination stabilize Pluto's path, its orbit remains relatively erratic. Minor deviations in Pluto's position or speed can lead to significant shifts in its trajectory over time. Despite this intrinsic chaos, Pluto's orbit remains stable for extended periods, suggesting that beneath its seemingly irregular appearance lies an underlying order, allowing for predictions about significant events, especially for planets with erratic orbits like Pluto. The challenges presented by the inherent eccentricity of these systems make mathematical simulations essential for understanding and predicting the future paths of celestial bodies. However, these models rely heavily on precise initial conditions and complex interactions, with even minor errors potentially leading to drastically different outcomes. The chaotic nature of celestial orbits, such as Pluto's, serves as a reminder of the dynamic universe we inhabit. While progress has been made in understanding space, Pluto's situation underscores our ongoing limited knowledge. Understanding the gravitational effects of massive planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system, demonstrating how each planet's presence and position can influence the stability and trajectory of other bodies within the system. Concerns about a potential collision between Pluto and Neptune, while intriguing, are largely unfounded based on our current understanding of celestial mechanics. The stability of Pluto's orbit, maintained by complex gravitational interactions with other planets, ensures that such an event is highly improbable. The intricate dance of celestial bodies in our solar system, including Pluto and Neptune, is governed by complex gravitational forces and orbital elements. While the prospect of a collision between these distant planets sparks curiosity and speculation, the fundamental stability of their orbits, upheld by the laws of physics, mitigate such concerns. Through ongoing observation, analysis, and mathematical simulations, scientists continue to expand their understanding of Pluto's remarkable journey through space, shedding light on the broader mysteries of our dynamic universe.